Fundamentals of HVACR, Chapter 10, Pressure and Vacuum. Objectives include: explain the concept of pressure and how pressure is expressed, explain the relationships among atmospheric pressure, gauge pressure, and absolute pressure, convert pressures to different scales, describe how gas responds to changes in temperature, volume, and pressure, solve for new pressure, new temperature, or new volume using the ideal gas law, and describe how a saturated gas behaves. Pressure is a fundamental physical property that is measured when servicing HVACR equipment. Hydronic, pneumatic, refrigeration, and air systems all depend on pressure differences to create flow. The compressor in a refrigeration system creates a pressure difference which causes the refrigerant to flow throughout the system. Pressure is a comparative measurement. It compares the force pushing on a surface to the area supporting the force. Pressure is uniformly distributed over the surface on which it is pushing. A solid exerts pressure downward because of gravity. Different states of matter exert pressure in different ways. Liquids exert pressure downward and outward because of gravity. A gas exerts pressure in all directions against the walls of its container. Fluid pressure is the force per unit area that is exerted by a gas or a liquid. Many people do not realize that air is a fluid. However, either a liquid or a gas can be a fluid. A fluid is anything that can flow. Some common units of pressure include psi, Pascal, kilopascal, and bar. The psi, pounds per square inch, is used in the inch-pound system to measure the pressure in car tires or refrigerant pressure in an air conditioning system. The Pascal is a standard unit of pressure in the SI system. It is defined as the force of 1 Newton per square meter. The Pascal is a very small amount of pressure. Pascals are used for measuring the air pressure inside ductwork or the pressure put on a house when performing blower door tests. The kilopascal is a larger unit of pressure, equal to 1,000 pascals. Kilopascals are used for refrigeration system pressure in the SI system. The bar is also an SI system pressure unit. It is equal to 100 kilopascals and is roughly equal to atmospheric pressure. Bars are used to report atmospheric pressure and are sometimes used in refrigeration system pressures. Pressure can also be measured by measuring the height of a liquid column the pressure will support. The higher the pressure, the farther up the tube the liquid column will go. Manometers are used to measure liquid column pressure. A manometer is basically a U-shaped tube filled with liquid. When pressure is applied to one end of the tube, the liquid level on that side drops while the liquid level on the opposite side rises. The difference between the two sides is your liquid column measurement. Mercury is used in manometers which are used for higher pressure readings. Atmospheric pressure is measured in inches of mercury. In air conditioning, we use mercury columns to measure vacuum. Water is used in manometers designed for lower pressures. Water columns are used to measure the air pressure in ductwork and the gas pressure in gas furnaces because the pressures in air ducts and the gas lines are much smaller. Water pumps often have a specification called head. Head is the height of water expressed in feet. It is often used in water systems and water pumps. Head is the height difference from the lowest point to the highest point. As the height difference increases, the pressure differences created by the weight of the water increases. An increase in the height that the pump must move water against generally decreases the pump's pumping capacity. Standard atmospheric pressure at sea level with an air temperature of 59 degrees Fahrenheit is 14.7 psi or 101.325 kilopascals. In mercury column measurement, atmospheric pressure is 29.92 inches of mercury, or 760 millimeters of mercury. Atmospheric pressure varies with altitude. The atmospheric pressure in the mountains is considerably lower than the atmospheric pressure at the beach. The atmospheric pressure also changes with the weather. Both temperature and humidity changes affect atmospheric pressure. Changes in barometric pressure, the atmospheric pressure, helps weather forecasters predict the weather. A barometer is a device designed to measure the atmospheric pressure. Barometric pressure is a term that is used for the current atmospheric pressure. The first mercury barometers were made by filling a sealed tube with mercury and inverting it in a dish of mercury. The atmospheric pressure pushed down on the mercury in the dish and supported the column of mercury equal to atmospheric pressure. This required a tube a little bit longer than 30 inches, since atmospheric pressure is around 30 inches. Warning, don't do this at home. Mercury is toxic. Immersing your hand in a pool of liquid mercury is no longer considered an acceptable or safe practice. The mercury barometer is not very portable. The aneroid barometer was developed as a more portable instrument. Its operating mechanism is an evacuated bellows called an aneroid cell. Under lower pressure, the bellows expand, and under higher pressure, the bellows contract. This movement is tied to a needle which indicates the barometric pressure. The pressure gauges commonly used by service technicians use a Burden tube to determine system pressure. A Burden tube is a flattened tube which expands when more pressure is put on it and contracts when pressure is released. This works similar to the party blowers. The gauges used in HVACR typically measure pressure compared to the atmospheric pressure. Most refrigeration gauges are calibrated with 0 equal to atmospheric pressure. Pressures above atmospheric pressure register as a positive pressure, while pressures below atmospheric pressure register as a vacuum. One problem with this method is that since atmospheric pressure changes from one place to another, and even with weather changes, the needle will not always indicate 0 at the current atmospheric pressure. There are two types of gauges used on refrigeration systems: compound gauges and high-pressure gauges. Compound gauges are used to measure pressures above and below atmospheric pressure. High-pressure gauges can only measure pressure above atmospheric pressure. Absolute pressure is the pressure without regard to the current atmospheric pressure. In absolute pressure, 0 means 0. There is no pressure lower than 0 absolute pressure. Simply stated, absolute pressure is the real pressure. We use the abbreviations PSIG and PSIA to differentiate between gauge pressure and absolute pressure. You can convert between gauge pressure and absolute pressure by either adding or subtracting 14.7. Absolute pressure equals gauge pressure plus atmospheric pressure, which is approximately 14.7. That means that PSIA equals PSIG plus 14.7, or using the shortcut method, PSIA equals PSIG plus 15. Going the other way, PSIG equals PSIA minus 14.7, or using the shortcut method, PSIG equals PSIA minus 15. Anytime you're using pressures to calculate things such as compression ratio or gas laws, you must convert PSIG to PSIA before doing the calculations to get a correct answer. For example, if you were to calculate the compression ratio of a compressor with the low side of 120 PSIG and a high side of 420 PSIG, the compression ratio would come out at 3.5 if you used these numbers. But if you converted them to PSIA first, the 420 PSIG would be 435 PSIA, and the 120 PSIG would be 135 PSIA. That would give you an answer of only 3.2 for your compression ratio. A significant difference when you're doing that calculation. A vacuum is any pressure less than atmospheric pressure. Vacuum is traditionally stated in inches of mercury on traditional Burden tube gauges. Since standard atmospheric pressure is 29.92 inches of mercury, a perfect vacuum would be 29.92 inches of vacuum. That means 29.92 inches less than atmospheric pressure. Standard Burden tube mechanical gauges show a vacuum down to 30 inches. This is because they can't really show 29.92. A compound gauge is not really a very accurate way of measuring vacuum. We'll discuss measuring vacuums more in the vacuums unit later on. When gas is confined, it pushes against the size of its container, creating pressure. If more molecules are put into the same container, the pressure goes up because now there are more molecules to strike the surface. The three ways that gas pressure can be increased are by increasing the quantity of gas in the container, increasing the temperature of the gas, or decreasing the size of the container. Many scientists have studied the behavior of gases and contributed to our knowledge of gas laws. Several scientists have published their findings demonstrating a particular aspect of gas behavior. Each law is named after the scientist credited with creating it. Pascal's law states that when a gas is confined, it exerts equal pressure in all directions. This means that if the pressure were measured from the outside, from the inside, from the top, or from the bottom, the pressure readings would all be the same. Boyle's law states that the volume of a gas varies inversely with its pressure if the temperature of the gas remains constant. This means that if the volume increases, the pressure will decrease, and conversely, if the volume decreases, the pressure will increase. This is one of the main operating principles behind compressors. The compressor compresses or reduces the volume of the gas, which increases its pressure. Charles' law states that the volume of a gas is in direct proportion to its absolute temperature, provided that the pressure is kept constant. This means that a gas will expand in volume with an increase in temperature and contract in volume with a decrease in temperature. Gay-Lussac's law describes the relationship between gas pressure and gas temperature. The pressure of a gas is directly proportional to its temperature with the volume remaining constant. This means that increasing the temperature increases the pressure, or decreasing the temperature will decrease the pressure. A combination of all the previous laws is called the ideal gas law. The ideal gas law makes predictions of gas behavior possible even when all of the variables are changing. The formula on the screen shows the relationship between pressure, volume, and temperature according to the ideal gas law. This relationship states that the original pressure times the original volume divided by the original temperature should give the same ratio as the new pressure times the new volume divided by the new temperature. For this formula to work, it is important that all values are absolute. So pressure and temperature must all be converted to absolute pressures and absolute temperatures before working the ratios. Fahrenheit temperatures must be converted to Rankine by adding 460. PSIG pressures must be converted to PSIA pressures by adding 14.7 or 15 if rounding. Dalton's law states that the total pressure of a gas mixture is equal to the sum of all the gas partial pressures in the mixture. This means that the total pressure of a mixture of gases can be determined by adding each of the individual gas pressures up. So putting a gas which creates 100 pounds of pressure in the same container as a gas that creates 50 pounds of pressure will yield 150 pounds of pressure total. This gas law has serious ramifications for refrigeration systems. If you end up with gases which do not belong in the system, it increases the operating pressure of the system and decreases its efficiency. It is important to understand that saturated gas and saturated gas mixtures do not follow the ideal gas law. At the saturation point, the molecules have enough attraction for each other that removing heat from them will cause them to condense to a liquid. This drastically lowers the pressure because now there are fewer gas molecules in the same space. Similarly, adding heat to a saturated mixture in a container creates more gas molecules in the same volume. This dramatically increases the pressure. The increase in pressure from heating a saturated mixture is much more dramatic than increase in pressure due to simply increasing the temperature of the molecules that are already there, as in an ideal gas. The ideal gas laws do not apply to saturated mixtures because the number of gas molecules in the space changes as the temperature changes. Hydronic, pneumatic, refrigeration, and air systems all depend on pressure differences to create flow. This is why HVACR technicians must be familiar with pressure and vacuum readings so they can properly install, service, and repair these systems.